Welcome to a new test and teardown video. This is also going to be a repair video, maybe even mostly that. This is a Martin Hot-Beam-04. I think it's like 15 years old or something like that. This is quite old, by the way. We have been super happy about it. It is a really nice and good product, but unfortunately, today it is taking the lab fuses and they are 10 amps. So how is that possible? I opened the unit and my first inspection will be the 3 fuses. See? So I pulled these fuses and they're all okay. They're only 4 amp. The 2 black ones to the right here, I put a little note. So those are 4 amps. And the other one here is 160 milliamps. So that's probably for the transformer and the logic and all that kind of stuff. But why is it taking lab fuses? That's 10 amps. That is a big mystery. How is that possible? By the way, this is, if you don't know what an infrared heater is and what it is doing, I can give a very short introduction. So that will be 500 watt filament bulbs each, and of course this unit runs these at a much lower voltage, so they only glow red. They're not as bright as the sun as it would be, and it will also melt down everything here if you power them directly from mains voltage. And this is of course why they just last forever. They're not in a socket, they're soldered in and all that kind of stuff. And then there is a filter here. The idea is you don't see the glow that powerful, but you get the infrared. So this is an infrared bandpass filter, so to speak. You can see here. And well, you can see here, you can of course see a little bit through it. And then the red glow is of course going through here, and you put your circuit board on top of this and back heat it to like 100 Celsius or something like that. Then it's much easier to hand solder, hand rework SMD components. So that is definitely what we're using this for. There's an external temperature sensor, and you can put this on your circuit board, and this way it will compensate for the thermal loss, or if there are big heavy components on your circuit board, and all that is pretty smart as well. There's a little display where you can go into a menu, and you see there's a little probe icon here. The idea is you dial the temperature on and off, or select temperature controlled or just power controlled. You can also turn on just those 2 or these 2, so it's all 4. So in 2 zones. And yeah, hopefully we'll get this up and running later today. It is not designed for any kind of service. This is probably, I've been a little bit angry about this earlier today, and that is because we got all sorts of components hidden here. We also got 2 transistors mounted at the bottom metal, and the pins from those 2 transistors goes through the board and is soldered under here. And that means if you take away those 2 screws, you're going to lose the 2 nuts. They're going to fly around anyway. So that is definitely no access as well. You can see some screws here, and they go in little spacers to those screws here, but we got many more of those screws, and here they are nicely accessible via those holes right here. But that is not the case with the other screws hidden in there, and there's another one. So I mean, to get this apart, I need to desolder all the bulbs, take these out, bend these, unscrew the reflectors, and then take out the circuit board. What kind of a nightmare is that? So that is my complaint, and I don't think that I will be able to desolder these here, because it looks like they go through the board and up again. so they do not desolder if something is wrong here. Oh, by the way, I really should show you the reflectors. How cool are they? If you see the reflections, you see the filament is like 3 times on each of the bulbs. So this is almost the same as having those 4 filaments times 3. I love it. This is genius. So yes, I'm both happy and frustrated at the same time. And what can it be? So here's my first idea to try and see what happens. I take out all the 3 fuses, and then I will try and give it a little bit of maintenance slowly using a variac. And then hopefully nothing's gonna happen. Let's just give it 20 volts. And I think it is in the position on. Let's try and flip this one. Is it now on? It's not using any kind of power. So far so good. And then I will take my thermal camera and I will put in the fuses, and then I will see where is something getting warm. I mean, just a few milli Celsius will be detectable using a thermal camera. So this is, I mean, it feels like cheating, but hey, if I find the error easy and fast, then why not? So that is some weird thing. Now the fuses they're in, it is turned on, and I try to crank up the voltage, and it's not using any kind of power. So this is 30 volts and it says 0.0. So I'm just gonna... Okay, so the beeper goes on here. Why is it doing that? Oh, that is weird. So there's a low voltage thing. So I cannot crank up the voltage. This was 50 volts. So it seems to be alive. Should I just give it 230 in full go? And I don't know, man. It took my fuses today. So here we go. Let's see what happens. This one should, of course, not turn on any kind of heating when it's powered on. And here is my variable voltage. So I can just crank this up to 230 volts. And I changed the fuses in my variac to 1 amp. So it shouldn't blow up and cause a lot of destruction. Let's try and turn this on. Oops. Fucking A. All lights is out. How is that possible? Really?
You okay?
Yeah, we're okay.
Oh.
Okay, so let's see how difficult is it to pull this thing apart. First I took out the 4 lamps, and you need to desolder them, and then I need to unscrew the reflectors, I expect, and then I could probably access the rest of the circuit board. I will see about that. Is it going? All those funky springs here, they press against the glass to hold the glass up. And that is because the glass is, of course, going to be very, very warm. And that is why they made it so that it is a little bit free. So there's a little bit of friction all the way around, so the glass can and the metal can move when it gets hot and cold and all that kind of stuff. Otherwise, it's definitely gonna crack. So what have we got here? We got some transistors, and those are soldered in. We got some other transistors under here that is screwed to the bottom. And here is a little resistor to change the voltages. How cool is that? And those seems also to be running a little bit warm, not that much. Here's another temperature sensor. That is maybe activated if the fans stops moving. I mean, of course you need to have a sensor here, right? Tantalum capacitors in an area that is supposed to get warm. I'm not happy to see tantalum here at all. This should have been ceramic. But anyway, I really don't know how to get in here with those transistors, but I will try my best and we'll see. So I'm still removing all those screws, and then I think this is a little regulator, and it's mounted here on the chassis. So this one also needs to be detached. I remove those screws as well. And then let's see if I can get the circuit board out, because we got this kind of stuff here, and then I need to desolder. I mean, this is just the most unservice friendly design as you can probably imagine. It is most likely designed just to be thrown out if it's not working, but I want to give stuff a chance, and those are really, really expensive, so that is also a very good motivation. It is still driving me a little bit nuts, this unit. See? Now we can lift this, and we see some wires, and we see some transistors hidden in here. So to be able to lift this some more, I mean, I need to desolder the wires down there, and they are not that easy to access either. Why this complicated? Well. I'm still poking around with this thing. Finally, got the connectors removed, wires removed. I want to add some solder points here, so it's easier to solder in the wires without having to cause damage to the circuit board. Also, there's a connection from mains in to the circuit board, and then it just goes up to the switch. This is a little bit stupid. It's much better just to take the cable directly to the switch and save the wires to the circuit board there. About the problem we are having is a voltage, a mains voltage to chassis, and this way to protective earth, and this is what is causing my problem. And here is protective earth. It is, of course, chassis, and then there's a track, and then it goes over here, and then it goes to this screw, and that is, of course, to have all the reflector metal here proper grounded in case one of the bulbs explode or filaments goes all over the place. Of course, you want this piece of metal to be carefully grounded, and then you have your protection. So all that is fine. And I see a little resistor and a capacitor, and this goes to the secondary low voltage side. So I don't think it is that. But here on the primary side, we got the two red capacitors, and they are connected to protective earth. And I believe one of these goes to, or both of them goes to both sides of this little EMI filter. We also got some capacitors here and here, and I think they sit on the input and the output of this filter. I want to double check all that as well. But then here is what I think is another possibility for the problem. Let me zoom in here a little bit better. See, here we go. Those two, they are TIC 263, and that's a triac. So 400 volts, 25 amp triac each. So that is some hefty power here. Look at that. The center pin is mains voltage. There's no isolation or anything like that, right? So this is just mains. And then the sensor point here is, this metal point here is also connected to that mains. But there is a little isolation screw that goes through here. I mean, this is probably the most likely place where we could have this. So I want to unscrew these and verify what it could be. Maybe change the screws to nylon screws, and this way it will give me a lot more margin. The thing is that there's not a direct connection. There's like a very, very close connection. So when the voltage is high, then it sparks over and causes all the problems that we are having. Or could also just fix this and change those capacitors here, and then do another test and then see if we have found it. I am super happy to announce I have found it. Here you go. If you look inside this hole of the right one, you can probably see the little sparky black sparks, and we got some signs of it in here in the hole. And the thing is, there's this hole, the edge of this hole is quite sharp. All right, and then see the other part here. Here is also a sharp hole, and you can even see the spark marks here. The distance here is also like nothing, and this one was not in the center. It was dislocated just like the other one here. So here is a potential short spark over to protective earth, and this again reveal the high importance of correctly protective earth of your instruments. Because if you did not have a proper grounding of an instrument like this, you could get you would have mains voltage directly on your chassis, and when you touch this chassis, you're gonna get electrocuted. So it is a good thing that we got this protective earth. Let me see, what can I do to fix this? That is the big question. I'll try and put in a few photos of this spark over spot, so you can see in more clear detail what happened. I will. What I've done here is I took a drill and see I made the hole bigger, but it's also countersunk the hole from the inside like this. And I also did the same with the triax, and this way this hole is of course now much bigger on the bottom side, just a little bit like that, right? So there's no sharp edge here that will dig its way through isolation. And the hole in the glitter discs they're using is like really, really big. So I changed these to a high voltage, I think this is a silicone. It's also a little bit thicker, but this is a high voltage type, and the hole is of course much smaller. And then I will add some varnish into the hole here, and also to the edge of the backside of the triax, so there is no exposed metal to jump over. This should give me a much better isolation distance, but it's still, I mean, according to rules and regulations, metal to metal, I mean mains face to chassis here, you need to have several millimeters, especially when there's not air, but some material touching. This should have been like 2 or 3 millimeters to perform to the standards we have today. But I mean, this is of course a very, very old product, so they didn't have the same kind of requirements back then, I would suppose. Today you'll probably have a ceramic disc or a circuit board or some other metal here, and then interchange from the triax to the metal here. I mean, this is definitely not the way to do it today. I also think I want to show about this little 5-volt regulator here. It had the same problem. The hole was really, really razor sharp at the edges, so I had to drill it a little bit like that. And here, that's the mounting hole for that regulator, and it was the way that those holes are made, you can see the other hole. Oh, damn it. Here we go. Can you see the other hole that is to the most right? It is razor sharp at the edges, so it pokes holes through the glitter disc, and the hole here is in the middle of the picture. I think it is also visible. So this is a design error, really. That hole should not have this problem. You can even see how it's bending. So I tried to just a tiny little here. Here's a 0 volts difference, by the way, so it's not super critical. But I don't want any shorts. I'm waiting for my varnish here to dry, and then I can continue. I cheated a little bit and glued the silicone pads. That's super easy. Now they're perfectly in the right spot. But I'm still a little bit concerned about this distance here, because it is, okay, it's a millimeter, so that should be good for 1000 volts. But I doubt it's a legal distance. I could, of course, add a, see, there's a little metal, I don't know. I could maybe add a little bit of varnish around the nuts and this top here, because this is the kind of distance I like to have, really. So while we are at it, why not fix all the design errors? There's another one. First of all, this little hole here is too small. So this switch is standing on the top, preventing the display from being nice and straight. So only if you make this hole here a tiny little bit bigger from the inside, then your display is going to be visible much better, nice and straight. See those two screws here? Those are M3, and I don't know if you can see this. Can you see the marks on the circuit board here? So that means the nut is sitting right there. I don't know if you can see this, but the isolation distance, I mean, if this works or not, depends a little bit on how is this screw oriented. Here you got probably just not touching, but if it's like this, oops. I mean, how close is this? I don't know. That is not so good design. So if you put a plastic washer in here, then you have a nice safe distance, and then cut this pin. So if you have problems with some of those switches not working, that is probably the case. And there's another safe distance safety issue, and that is the washers they're using under the mounting screws here. I should probably just show you one of the other screws. You can see here. Can you see this washer, how big it is? So let me take one of these and put it here. Can you see what I'm trying to show? The SMD components. I don't know if I can put it at the same time in the middle. Can you see that? Depending on the accuracy, here we have a potential. I mean, this is not tip-top quality. Here you got really good, nice, safe distances, and all that is quite all right. I mean, but yeah, they just didn't do it all over the place. Another thing that bothers me a little bit in the daily usage. I mean, I really love this tiny little button here, but there's just some sort of a mismatch. Maybe it's not the original, but it has always been like that, right? This shaft is just way too long for this tiny little button, and it's really, I love this one, but when everything here is assembled, it just sticks out at the end of this, and you see half of the shaft through here. I mean, this is not so, this kind of, pro level you would expect from a product this expensive. So I mean, I want to go and cut this shaft 5 millimeters shorter in this way, but you can buy them shorter, so it's not, there's probably just a wrong part number somebody ordered. But when you do this, then it's gonna go in like that, and it's gonna look much better. You see? That's what I'm saying. This one goes over here. See? Now the display is nice and straight. I added a little isolation here, so it is not a problem. Yeah, also I cut the shaft. You can even see here the marks. This is where the shaft touched this front plate before, and this is only because I grinded or cut a little piece here from the back. So now the switch go out and the board is nice and straight, and well, I should probably have made it whole a little bit bigger. But anyway, this is where we keep it. I could also have made this shaft about 1 millimeter shorter, because see, still here a little bit. I mean, let's keep it like that and not overcomplicate things. It's already taking a little bit, going a little bit out of hand here. Oh yeah, this is another one for that one. Better do it right, you know. So I feel a little bit lucky now. Everything here is assembled and ready to be tested. So let's try and power it up and see if we are a little. Yeah. All right, are we ready? Yes, we are ready. Here we go. Here we go. And it seems to be working. After a few minutes, the fans, they stop rotating, and now it is in idle, what's waiting for user input. So we can, of course, push start button, or we can dial around with the menu. Oh, teach, edit, manual mode, config, or the different programs. We can go in manual mode, and then you can select a temperature and how long time, Celsius, and here how many minutes up to. Oh yeah, 8 is the maximum. So if I enable it to go 150, it's going to use the external temperature sensor like this one if I hit start. So let's see what happens. I will put this temperature sensor directly on top of one of the heaters, and let's see what happens. Probably gonna take the fuses here because it can pull a lot more current than my little Vario can give, but then it's only going to be the local fuses here that's gonna blow. So let's try and see what happens. Oh, here we go. It uses 300 watts, and my temperature sensor here is, oh, I put the temperature sensor directly to the glass, and then, oh yeah, then it turns on and off like this. And of course, normally you won't see this light up this powerful, because there will be this infrared filter on top of it. But here I have it without this filter. Damn it, this is bright. I think they take both of these 500 watt bulbs in series. So this explains I'm using about 200 or 250 watts at the moment every time it pulses. But anyway, the unit definitely works again, and I am super happy. So now I can just continue the last and final assembly. We can turn this off again, and that's it. So there's only one last little detail I want to show you, and that is if you turn this on without the temperature sensor connected, then it goes into another mode of operation. So now it's not temperature controlled, but power controlled. So I didn't figure out any other way to switch between power and temperature mode. So now you can just say how many watts you want. So let's just say 50 watts. And then if you hold in this switch, you can, is it down here in minutes? Yeah, here we go. So this is the back. So the heater is two different elements, right? Back, all or front. So let's just use the back one and say okay. And then you hit start. So now it is using 50 watts, and you can see it's blinking real nice and fine like that. And of course it is not controlling the temperature in any way. And it's also using a little bit of watts by itself. So the total here is 55. And it's probably too hot to touch in any possible way. And this one warms up really, really fast, almost instantly, because it's infrared. And this is probably enough to do a light SMD work, and it's not going to damage any kind of components. You can just put whatever component you like, a circuit board you have, you just stick it on. And the cool thing about it is the distance to the circuit board. If you got all sorts of pins or all sorts of long components sticking up, it doesn't really matter much. The temperature you get on this circuit board here is more or less the same compared to if you had these pins or not, because it's infrared radiation. I really like this idea instead of the direct connected heating plates. But here you don't have to worry about the temperature sensor, so it can be an advantage or a disadvantage depending on the type of work you want to do. Anyway, that was a little bit about heat plates and this particular type of heat plate for SMD rework, and now it is perfectly fine. I even cleaned it a little bit so it's super nice and smooth. But thank you very much for watching. Hope to see you soon again. Bye.